Part C, next one up. The heat transferred to the boiler if the adiabatic pump absorbs 4 kilojoules per kilogram. So here we go. We are at the pump. Okay, pump is where we go from 4 to 5, 4 to 5, from 4 to 5. And we have an extra piece of information. That is that the difference between the energy states on the 4 and 5 is 4 kilojoules per kilogram. What the problem statement is telling us is that this pump, this Q in here, the amount of energy it requires equals 4 kilojoules per kilogram of water that it pumps through. Okay, and that information is super valuable because then we don't even need to go to that way I said before of going both ways. It's already giving us a piece of the puzzle that we can now relate state 4 to define state 5 completely. Okay, and then with that piece of information, we can go ahead and say, okay, so if I want to find out what is the heat transfer to the boiler, all I need to do is first find the pump, use the pump information to define state 5, and then obviously do this control volume around the boiler, in which I have Q in going here, enthalpy 5 going here, and enthalpy 1 leaving my boiler. So let me go ahead and grab this. We're going to use this in a little second. But first I need to find out what is H5, and for that I'm going to use the fact that I know that my pump requires 4 kilojoules for every kilogram of water it pumps. And if I do an energy balance on the pump first, I should have done that. So let me do this. Let me do this first. Come on. There you go. All right. So that's my boiler one. And then for my pump, what do we have on my pump? I have state 4 going in. So enthalpy 4 going in. I have work in that I need to put so that this, so that we can get the pump to work, right? And then enthalpy 5 coming out. So the energy balance there is enthalpy 5 will be a combination of the work I'm putting in and the enthalpy of state 4 that's going into my system. So I don't need to change anything in that equation. All I need to do is relate the 4 kilojoules per kilogram with the 188, right? Yeah, 188.5. 188.5 kilojoules per kilogram. Okay, all good there. So this means that this is going to be 192.5, and that is also in kilojoules per kilogram, and that is the enthalpy on state 5, which is one of the things that I need to be able to do this energy balance here. And this energy balance, once again, no mistakes. We have these two guys going in, this guy going out. So therefore, this means that enthalpy 1 has to be equal to enthalpy 5 plus heat going in. We're interested in knowing the heat going in, so therefore heat going in will simply be the enthalpy 1 minus enthalpy 5. We have all we need. Enthalpy 1, do we have enthalpy 1? I forget. We don't, but we do have specific volume. So next up is, what is enthalpy 1? Pressure of 2,000 kilopascals, so 2 megapascals, and specific volume of 0.1255. So here you go, saturated water. I'm looking at 20 bar, same thing as 2,000 kilopascals. I'm looking at the specific volume, and I'm looking at this number here. And I'm wondering whether the 0.12 something? Yep, if this number is greater or smaller than this guy here, and it's greater. So if it's greater, this means that state 1 is a superheated state. So do superheated state. So therefore, that's no good. I need to use a superheated steam table, and I need to use a superheated steam table at 20 bar or 2,000 kilopascals, and I need to look for a specific volume of 0.1255. And if you look closely, you're going to note that we do have that value right here. And therefore, the temperature of state 1 is 300. Therefore, the enthalpy of state 1 is 3025. Right? So this is my state right here. This is my state 1. State 1. Okay, so all good. 3025. I'm going to go ahead and do this. 3025. Superheated state. So there, and I could put the other, for instance, internal energy is 2774. I could fill in all these properties for all these guys if I wanted to, right? As long as I have the state defined. So 3025 minus the work we just found, 192, sorry, not the work, state 5, 192.5 units are the same, so no problems there. Qn is 2832.5. 2832.5, and that is kilojoules per kilograms. Okay, so for every kilogram of water going through my system, I have 28, or to my boiler, through my boiler in this case, 28.32. Okay, super important. This is a step in which we're gaining energy, right? So let's go back to our drawing. We're putting some energy here, probably, steam power plants like to use coal, natural gas. So we put in natural gas, we burn it up, we use that energy. This is the Qn coming out from this fossil fuel. We use that energy to boil the water, so we're giving energy to the water. The water then goes to the turbine, we generate our work. It comes out part saturated mixture, parts saturated vapor, part saturated liquid. Then we condense the whole thing, make it all liquid. Then we can pump it through the boiler again. That's the whole cycle. All right, part D, the heat transfer in the line between the boiler and the turbine. So right here, note that we have, between the boiler and the turbine, we have two different states. And if the states are not the same, it means we're losing some energy as we're going from 1 to 2, right? So there's nothing here per se. There's no, no component. But unless we have a system that's 100% efficient, there will be some losses in this line. And they're asking precisely what are the losses as we go from state 1 to state 2. So that's super easy for us to do. We've done a lot of this already. This is just one under one. As we're going from, let's just do a little pretend component here. As we're going through the line, we have the enthalpy 1 as the input, the enthalpy 2 as the output, and then depending on the difference, we're going to have something going in or going out. Something going in or going out, right? And this energy is what we can determine. That's going to be lost in the form of heat, so we can say it's Q. And I, assume it's going to be Q out, but we can be sure, right? So how do we do that? What we do is, if it's Q out, it's going to be this, right? And if this is the case, how do I set up this equation? I'm going to say, well, H1 equals Q out plus H2. What is the other option? Well, I can assume heat is going to be going in. If that's the case, then my equation becomes, I'm doing it in blue so that no one is confused. H1 plus Q equals in equals H2. I can do both ways, and if I get a positive number by doing this way, it means this is right. If I get a negative number doing this way, I mean this is wrong, and then I need to flip and say, okay, this is Q in. Likewise, over here, if I do it like this and I get a positive number, then this is right assumption. If I get a negative number, it's a wrong assumption. I need to flip it. Okay, so it doesn't really matter. Whatever rocks your boat. We can do both here, but this is pretty straightforward. So Q out, in this case here, will be simply H1 minus H2. H1 happens to be the, what did we just find a second ago? where is it? 3025. 3025, the energy after I leave my boiler. And 2 is 3002.5. 3002.5. So this is going to be a positive number. In fact, that number is 22.5. 22.5 kilojoules per kilogram. right? So indeed, this is the right assumption. Energy's out. Okay. Again, and this needs to be super clear to students, right? If I'm saying Q out, I don't really need to worry about any sign. Okay. If I'm saying Q out, get a positive number, that is an indication that I was right when I assumed Q is going out. Right? Sometimes your professor might want the answer in like this, right? And this is an indication, also an indication it's going out. So if you do this, and you do this, and you do this, that's the same thing. Okay? Forget the units here, whatever the units are. Okay, these two things are the same thing. Using that negative and giving the direction with that little subscript, that's the same thing. So I generally like to do with the subscript because it's easier for students to relate to what we're saying. Okay, that out of the way, this is the answer to part D. And then last but not least, what is part E? Compare the turbine and the pump work and comment the results and find the mass flow rate through the plant if the power developed by this turbine is 3,000 kilowatts. Okay, so one thing at a time. Let me just write the power going through this is 3,000 kilowatts or 3 megawatts. Let's first look at the pump and so the pump requires 4 kilojoules per kilogram and the turbine is generating 638. Okay, so note it's not even an order of magnitude difference, it's 2 orders of magnitude difference. And that makes a lot of sense, right? Because the whole idea of a power plant is that the work you're putting in, that is the work that you're giving to the pump, generally in the form of electrical energy, is way smaller than the work you're getting out of the turbine, right? And how is that possible? Doesn't that violate the first law? No, it doesn't. Why? Because the actual energy is coming from this guy here, right? So if we do an energy balance in this whole system related to all these things, we need to say that the work going out plus the heat going out needs to be equal to the heat going in plus the work going in, right? In other words, then we're not violating any of the laws. So this is super small, this is super big, so therefore these guys are responsible for balancing it out, right? We need a lot of energy going in, little heat going out, so that the first law is still kept, not violated. All right, so now on to the last bit, which is what is the mass flow rate if we have 3,000 kilowatts being generated? Well, if we have 3,000 watts being generated, it means that we have the difference between, precisely what we're talking about, right? The difference between the Q in, Q out, and pump is leaves over the 3,000. And this has to be gained by multiplying the kilojoules per kilogram that we had before by a mass flow rate. And the mass flow rate we know is kilograms per second. And what happens here is that we're left with kilojoules per second, which is the same thing as a kilowatt, right? So if this is the case, then this is very straightforward because work out equals 3,000 kilowatts. And we know our turbine is operating at 600 and, what did we find? 638.4. 638.4. So this needs to be equal to the work of the turbine times a mass flow rate. And if I want to find the mass flow rate, all I need to do is take the 3,000 kilowatts and divide that by the work out. I happen to know the work out, so this is going to be just the 3,000 kilowatts divided by 638.4. Okay, so now we just need to ensure that we have the right units. So this is kilowatts here. This is a given, so let's do it here. So we have kilowatts on this side, and over here we have kilojoules per kilograms. So therefore, kilo and kilo go away. And the watts, I'm going to break the watts into, break this into joules per second. Okay, so that means that I can now break my joules with joules, and I'm left with kilograms per second, which is great, because that's exactly what I'm looking for. So the mass flow rate by doing that. The mass flow rate is 4.6992, and that keeps going. So let's go ahead and approximate that to 4.7. I'm going to say 4.7 kilograms per second, approximately. And that would be the amount of water that's going through my turbine every second. So every second, the turbine that we just analyzed is 4.7 kilograms of water is going through that turbine, and that is generating 3,000 watts, right? 3,000 joules every second. 3,000 kilowatts, excuse me. 3,000 kilowatts every second. Okay, so I hope this was useful. If it was, consider giving this video a like. Like I said in the beginning, it's not a hard problem per se, but it does require a lot of little steps, and it's very good for us to practice this idea of applying the first law, applying energy balance. So I hope it was useful. If you have any questions, as per usual, just leave them down below in the comment section, and we'll talk soon.